Thank you. Good afternoon. And as Danny mentioned, my name is Lee Bingham, and I'm joined by my colleague, Jack Kincaid. We are both engineers with the Software, Robotics, and Simulation Division at NASA's Johnson Space Center. And today we'll be going over the topic of lunar terrain visualization using Unreal Engine 5. So as many of you may be aware, we are in an exciting time in space exploration. With NASA's initiative to return to the moon, with its Artemis program, we are taking what was done with Apollo and building upon that with the knowledge and technology developed since then to not only return to the moon, but establish the first long-term human robotic presence on and around the moon. This program will demonstrate new technology and capabilities to assist with future exploration, provide the opportunity to further study the Earth and our moon, and inspire a new generation of space explorers, scientists, and engineers. So with this presentation, we will be providing information that details how we are utilizing Unreal Engine 5 to generate and visualize accurate lunar terrain. I will provide some background as to what and why we build simulations and models for engineering, and Jack will go into detail on the how we generate the lunar terrain and the trades we had to perform, and then we'll conclude with some information on how we model the various other aspects of the lunar environment. As part of the Software, Robotics, and Simulation Division, we understand that all simulations are approximations. With that in mind, we strive to ensure that our models and simulations are sufficiently accurate for its intended use. As with anything else, there is a balancing act. Our budgets aren't infinite, so we strive to balance fidelity with cost. The products that we develop are typically used in three general domains. One is to enhance the design of new vehicles and concepts. As such, we can model a prototype lunar rover or lander and test how they perform and the interoperability between systems and help provide insight to whether that design or component is suitable for its intended use. Additionally, we use our models and simulations in mission planning to ensure mission success and help minimize and mitigate risks. And finally, for training. Training crew by providing flight-like environment to enhance and develop their skills, as well as prepare them for potential contingencies. So why do we need to model the lunar surface? Well, as we prepare for the Artemis missions, there are a number of risks and unknowns that we must buy down, as well as developing the necessary tools for that analysis, mission planning, and training. These include things like providing the topography for lander approach trajectories, or optimizing something like a rover traversal, taking into account constraints such as energetics, visibility, and communications. We also need to generate a representative environment as we train our astronauts for their lunar-focused missions and extravehicular activities. At NASA, we are focused on engineering-driven design, where we go through the rigorous process of requirements traceability and the verification and validation efforts to ensure that our models and simulations can be used to help increase mission success. As an example of this effort, we have gone back and used our tools to recreate imagery from the Apollo missions, as well as those taken from the narrow-angle camera on the Lunar Reconnaissance Orbiter. And we use those to determine if our representation of the lunar surface is accurate. And this accuracy versus artistry is where we typically diverge from game-focused applications. We prioritize traceability, accuracy, and fidelity as we develop our models and sims. So to generate our lunar terrain in Unreal, we need data. The data we use is provided by the Lunar Reconnaissance Orbiter, or LRO, which is a scientific robotic mission which was launched in 2009 with a mission to map out the lunar surface. One of the primary instruments on the LRO is the Lunar Orbiter Laser Altimeter, or LOLA, which provides precise global lunar topography and geodetic grid that is then used to generate the digital elevation models, or DEM files, that we can then use. One of the tools that we use to read and process these DIM files is the Geospatial Data Extraction Library, or GDAL. These DIM files are typically in the .tiff file format, which contains coordinates, the corresponding elevations, and a coordinate reference system, or CRS. So the following video provides a quick overview of our lunar terrain visualization using Unreal Engine 5. We are focused on the areas on and around the south pole of the moon, where the lighting conditions are quite dramatic and can vary drastically depending on the date and time, with roughly 12 degrees of azimuth change over the course of an Earth day. The long shadows and terrain features cast by rocks can make this area an extremely challenging environment to navigate and explore. In this area near the South Pole, the sun only gets about 3 degrees above the local horizon. And as you can imagine, craters can be huge unknowns with their depths and potential hazards unknown and within shadow. The use of Unreal Engine 5 allows us the opportunity to use many of the unique features and capabilities present in the renderer to assist with the development of our simulations. As a sense of scale, you can see that we are able to render large areas of the moon with a fidelity that matches the source and available data. Thank you, and I'll hand it off to Jack, who will go into detail on how we generate this lunar terrain.
Hi, everyone. My name is Jack Kincaid. I'm a software engineer at NASA's Johnson Space Center, and part of my work has been to research the use of Unreal Engine 5 as a tool for lunar simulation development. Today, I'll be presenting to you a few of the lunar terrain generation methods that we've been experimenting with. Okay, so in summary of what we're going to talk about, there are 3 primary pipelines that we've either utilized or developed. The first of which is the landscape mode in Unreal Engine. The second is by generating nanite meshes of our lunar terrain entirely within the engine. And the third is a clipmap-based dynamic mesh rendering approach. Okay, so first off is the landscape mode. I'm assuming most of you probably have some level of familiarity with this feature of Unreal Engine. It's very easy to use, and you can efficiently generate very vast regions of terrain. For us, there was really just one additional step we had to take in order to use our source LRO DIM data in the landscape system. And that was simply to convert it to a usable file format. By default, the landscape mode in Unreal Engine does support height-map importing. However, they have to be in either a PNG or a RAW file format. Now, most of our DIM data is generally stored in a TIFF, which means we have to convert to a PNG before we can use it. To do this, we use the GDAL tool, or the Geospatial Data Abstraction Library, which really just lets us run a series of commands on our various raster data products. Using GDAL, we run a GDAL translate command, which converts that TIFF to a PNG. We can then simply use the import from file functionality, and we'll have our data in the landscape system. There are 2 parameters that you'll have to configure, the first of which is the XY scale, and the second is your Z scale. Now, your XY scale is actually a factor of your pixel width, and that pixel width can be found if you're using GDAL with a GDAL info command. Now, our pixel width is generally provided in meters, which allows us to simply multiply that given value by the XY scale found in by default for the landscape mode. This is primarily because by default, Unreal Engine assigns a 1 meter distance between vertices. So once you have that, you can then proceed to calculating your Z scale. So this is when things get a little bit different, primarily because the landscape mode in Unreal Engine utilizes a 16-bit height range for their landscape elevations, and most of our DIMS data is stored in a float 32 data format. This means that we have to convert, and we will lose some precision along the way. We can use this equation here to maintain our relative scale, where we take our total range, so the minimum elevation plus the maximum elevation. If you're using GDAL, you can once again run a GDAL info command to get those values. Then you multiply by 100 to convert to centimeters, and you divide by 512 to get into that 16-bit range from -256 to +256. Once you have that, you can then select import, and you'll end up with a generated landscape similar to the one seen here. And now, like I said, this tool is very easy to use. We are able to efficiently generate pretty large regions of terrain, approximately 40 kilometers squared at 5 meters per pixel, and it remains relatively performant. Additionally, the entire generation process only takes a few minutes. This leads me into some of the additional benefits of this feature, which first off is its integration with the world partitioning system. So you can actually establish a series of streaming proxies for your landscape, which provide you some additional tiling functionality so that you can stream in certain areas of your terrain based off of where your player is located. Additionally, the system provides a series of landscape editing tools, which can be used to sculpt additional features or add certain detail in some areas. However, for us, the most prominent benefit to this method as it applies to our specific use case of lunar terrain generation is the fact that it's integrated entirely within the engine. So it doesn't require the use of any external plugins, and every time we update to the next official release, we also receive any updates that were made to the landscape mode. That being said, there are a few limitations. First off is that N16 heights for the landscape elevations. Since we are trying to replicate real-world conditions with the highest degree of accuracy as possible, that loss of precision from our source data to our rendered representation is not ideal. Additionally, it's pretty difficult to add accurate lunar curvature, especially after the landscape's generated. There are some methods to do it, such as with a material position offset, but it's difficult to ensure its accuracy, and it also adds an additional performance overhead and makes collisions a little bit more difficult. So we decided to continue exploring our terrain generation methods to see if we could develop something that allowed us to maintain our precision from our source data to our render data, and also allowed us to include accurate lunar curvature. This led us to the development of a Nanite mesh lunar terrain implementation. So I'm assuming most of you probably are familiar with Nanite. It's Unreal Engine 5's new virtualized geometry system that basically lets you render very highly detailed meshes at minimal performance cost. We decided to take advantage of this system by importing our DIMs directly into the engine and using that DIM data to generate static meshes with Nanite enabled. A little bit more about this process. It does require the use of one external plugin, specifically the Unreal GDAL plugin developed by TensorWorks, which is pretty cool because it lets us actually run GDAL commands entirely within the engine. So using Unreal GDAL, we can get all of that DIM data, such as the dimensions, the coordinates, and the actual raster elevations, and use them to create a grid that will represent our mesh's vertices. We can then proceed to generate all the additional mesh information, such as the normals, UVs, tangents, and so on. Once we have all that, we send it to one final function that creates all that static mesh UAsset info, as well as enables Nanite. So there are a few things to note. We learned some lessons during this method where, first off, we found that no individual mesh could be greater than 2 gigabytes in size. And some of our source data can range anywhere from 300 megabytes all the way up to 6 gigabytes. And that's just the source data without any of that additional mesh information, which increases its size. So we had to institute a pretty aggressive tiling system so that we could still get all of that DIM data into the engine and represent individual Nanite mesh tiles. So what we did is, with our tiling system here, you can see an example of a 300 megabyte float 32 DIM that was imported and resulted in 9 Nanite mesh tiles. Now, 2 more things to note with this system is the generation process takes a fair amount of time. We found that for some of our DIMs, just a single import can take anywhere from 1 hour to 1 day, depending on the size of your source data. Additionally, it utilizes a fair amount of virtual memory, with some of our larger DIMs taking hundreds of gigabytes to complete virtual memory just to complete that generation. However, once the meshes are generated, they're extremely performant with pretty much no decrease in our overall frame rate, regardless of how many terrain meshes we added to the level. So that being said, now that they're generated, we're able to distribute them to any number of levels or additional projects. Now this video here demonstrates the optimizations that Nanite performs on our terrain as the camera gets closer or further away from the lunar surface. Additionally, we're able to take advantage of the optimizations with virtual shadow maps that allow us to render very long shadows of tens of kilometers in length that remain visibly accurate the further away you get from the lunar surface. Okay, so in summary of the benefits of this method, it is very performant. So we were able to generate large regions of nanite meshes without a significant decrease in our frame rate. Additionally, we're able to take advantage of Unreal Engine 5's double precision feature on those render static meshes. We were also able to resolve the two primary concerns with the landscape system, which were that loss of precision and the lunar curvature. Since we are generating directly from our DIM data, we maintain our actual precision with our source data. Additionally, we incorporate lunar curvature during the mesh generation process. So we apply a planar to spherical transformation as the mesh is being generated. This means that our final mesh all have the same curvature built in, and that remains consistent as they are distributed to various projects. However, it is not a perfect system. There are still some limitations, the first of which is that lengthy generation time. We do occasionally receive updates to our terrain generation methods, which force us to have to go back in, regenerate all of our nanite meshes, and once again, like I said, that can take a relatively long time. So not an ideal workflow. Additionally, Nanite currently has limited PC platform support, primarily to Windows-based operating systems, and we have to distribute to additional operating systems occasionally, such as Mac or Linux. And then finally, the relatively high memory usage. We found that not only during the generation of the meshes, but also during the loading of the scene, we weren't able to actually run the level on any systems that had less than 32 gigabytes of RAM. In summary, this method does provide the highest degree of fidelity with the best performance, but it comes with the strictest hardware limitations. So we decided to continue exploring our terrain generation methods to see if we could develop something that was a little bit more scalable to match hardware capabilities, and a little bit more flexible to provide support to additional platforms. This led us to the development of a clipmap-based lunar terrain system. Now, if you're not familiar with geometry clipmaps, they're a terrain rendering system that entails a series of decreasing resolution grids extending away from your player or your viewpoint. As your player navigates the level, the clipmap mesh will actually update to match the player's change in position. We decided to implement a similar system in Unreal Engine 5, where we generate a clipmap grid, and we populate the vertices with DIM data that we load into the user's memory. In this video, you can see the clipmap grid, the wireframe actually updating as the camera traverses the level. You'll find that when the camera reaches a fixed distance, it triggers a mesh update and all the vertices will find new positions. Now, this method utilizes two external plugins, the first of which is the Runtime Mesh Component plugin developed by Triaxis Games, and the second is once again that Unreal GDAL plugin. Additionally, we make use of the in-engine plugin, the procedural mesh components, to provide collisions anywhere on the lunar surface. So the key aspect of this method is we wanted to develop something that was fully configurable by the user to meet their hardware requirements. This means that we had to provide them a way to modify the fidelity and the size of their clipmap. So to do this, we provide three parameters that the user can configure. The first of which is the level count, and that's simply the number of grids present in your clipmap. The second is the grid width, and that is your actual vertice count per side of each grid. And finally is the starting resolution, and that's going to be the highest resolution found in your clipmap, which is present in that base grid. For us, we choose 20 centimeters per pixel because that is equivalent to the highest resolution terrain data we have. That value falls off by a factor of 2 with each level that you increase to. Now, all of those values are fully configurable by the user, either in runtime or in the editor for development purposes. So in addition to being able to configure the fidelity of their clipmap to match their performance constraints, we also wanted to allow the user to regulate their memory usage, because we are loading all of these height maps into the user's memory, and as I mentioned earlier, they can be relatively large files. Our standard distribution is about 15 gigabytes worth of height maps. And however, the user can actually regulate how many of those height maps are loaded. What it does is we just have a folder in the user's project directory where all those height maps are stored, and the system will load any height maps that are present in that folder. So if the user doesn't need fidelity in certain areas of the terrain, or they are encountering memory constraints, they can simply remove height maps that they don't need. In the same sense, if they want to add fidelity to certain areas of the terrain, all they have to do is add their DIMs to that folder. Now our system establishes a precedence for DIMs that have overlapping coordinates. We use Unreal GDAO to determine the actual coordinates and resolution of each loaded height map file. And for any overlapping DIMs, we'll find that we'll always use the highest resolution DIM in place of its lower resolution counterpart. This ensures that we have the highest resolution terrain anywhere on the lunar surface. This video here is approximately 6 different height maps. They are ranging in resolution from 100 meters per pixel up to 20 centimeters per pixel at that starting location. We also do have collisions anywhere on the lunar surface. We have 2 primary methods of incorporating collisions. The first of which is simply by forcefully adjusting the actor height if they're about to collide with the lunar surface. We really only use this on the actual player. Secondly, we utilize localized procedural mesh components on any actors that need to have physics enabled. Now what this is we just attach a procedural mesh component to the actor. They're generally relatively small, like 20 meters squared, and we'll dynamically drive the vertices of that procedural mesh with our height map data. So as the actor moves around the scene, the mesh will update for them to collide with. So a few additional details of this terrain implementation. Our clipmap grids never exactly align with our DIM data, which means that we have to interpolate. So every vertex of our clipmap grid will actually find the 4 nearest vertices of our DIM data, and we'll interpolate that value for the height of that vertex. We do a similar process with our normals. However, we utilize the actual slopes of our source data. So the camera's update rate. We chose to not update based off of tick, primarily because there'd be an unnecessary amount of performance overhead when the camera wasn't moving. So instead, we update after the camera's moved a fixed distance that we refer to as the update rate. Now this update rate is calculated as a factor of your clipmap's base grid's width and one of your larger levels resolution. We found that we needed the update rate to be less than our base grid's total dimension to ensure that our camera remained relatively close to the highest resolution terrain. However, we couldn't just use that value because we ended up with a fair amount of visual artifacts in the far field of our terrain. So that means we had to use an actual update rate that was also a factor of one of our larger levels resolutions. This ensures that there's a higher percentage of already existing vertex positions for that updated clip map vertices to move into. So in an attempt to compromise, we choose the largest level's resolution that is still less than our base grid's total width. And we set that equal to our update rate. Okay, finally, so we choose all of this mesh updating actually happens on a separate thread. This is a capability provided to us by the runtime mesh component. While that is nice because it prevents us from hanging the rendering thread, it also means that there's potential for the actual mesh updating to slightly lag behind the camera's position if the camera's moving at a rapid rate along the terrain. So some of the benefits of this method, we were able to carry over all of the primary benefits of the Nanite mesh implementation, which were the generated directly from DIM, the use of double precision, and the incorporation of lunar curvature. Additionally, we resolved our primary concerns, which were the scalability to match users' hardware requirements and the platform flexibility. The Clipmap system is fully scalable to match the user's hardware limitations based off of either their performance or their memory usage. Additionally, we have relatively flexible platform support with current support for Windows, Mac, and Linux operating systems, as well as virtual reality and in-display implementations. There is the potential for some visual artifacts to occur. The first of which is also when you have that fast camera speed along the terrain. Sometimes when the mesh updates, if it's updating really fast, you'll actually see some artifacts in the distance of your terrain. Additionally, if you're on a system that has limited hardware capability, and so you have to use a low level count for your clip map, you might actually see some partial shadows. And that's primarily because the actual features needed to cast those shadows might not be fully rendered themselves. And then finally, if you're in a lower resolution area of the terrain, such as 50 meters per pixel, and you teleport instantly to say like a 20 centimeter per pixel area, you might actually see that terrain briefly load in. Okay, so in summary, we've either utilized or developed 3 different terrain generation methods in Unreal Engine 5. They all have very different level of detail handling systems. However, they all result in extremely similar visuals. So when it comes down to choosing a method to spend time implementing or just utilizing, it really becomes a matter of what is your use case and what is your utility for this system. For example, the landscape system is very efficient and easy to use. And as long as you don't really need that double precision accuracy on the landscape elevations, then you might be able to go with that system. However, if you need a bit more precision as well as performance, you might want to look at a Nanite mesh implementation as long as you can accommodate that hardware limitations. And then finally, if you want to look at developing your own implementation that you can modify the scalability as well as the platform's flexibility to meet your needs, while also maintaining the fidelity of your source data, then you could look at implementing something like a clipmap-based approach. Okay, so now that was a brief overview of what we've done so far with our terrain generation. Now we're gonna talk a little bit to some of the additional features we incorporate into our environment to help add some additional fidelity. So lunar curvature, I've talked a bit about how we do this. Here I kind of wanted to stress its importance. A lot of lower fidelity lunar simulations tend to simply leave out curvature, especially if they're in smaller regions, primarily because their effect is often relatively insignificant for small areas of say like 10 kilometers squared. However, with the advent of new technology like Unreal Engine 5, we're now able to render much larger areas of the terrain with an increased level of fidelity. This means as our scale increases, so does the effect of curvature the further we get away from our origin. For example, here's approximately 4,000 kilometers squared rendered at a starting precision of 20 centimeters. And you can see the effect of curvature the further away you get from that actual origin point. So I just wanted to emphasize, if you are developing a large scale simulation, to look at incorporating curvature if you wanted to ensure that your shadow and terrain rendering are as accurate as possible. Okay, now I'm going to hand it off to Lee to talk a little bit more on some of the additional features that we add into our environment.
Thank you, Jack. So another key feature for our lunar surface environment modeling are rocks and craters. In general, the best available data from the Lunar Orbiter Laser Altimeter is 5 meters per pixel. This essentially boils down to several 5 meters on a side squares that make up the lunar surface. But in order to create a more representative environment, we enhance this data with crater and rock distributions, with input from the lunar surface science community and our JSC-based Astromaterials Research Exploration Science group. These craters are then embedded into our DEM files, and by doing so, we upscale this data to essentially 20 centimeters per pixel. Because we place hundreds of thousands of rocks in any given site of interest, we enable Nanite on all the rock meshes to help with performance. We make use of Unreal's Lumen capability to increase the fidelity of a representative lighting. The bounce lighting increases crater visibility when light is being reflected from objects like a spacesuit or surface assets like a rover, a habitat, or even the lunar surface regolith itself. This capability helps us illustrate the depth of craters as well as the impact of the sun's intensity without atmospheric scattering. These are approximations, but they do improve the realism of how light and shadow can impact your mission environment. In line with these shadows, we are using virtual shadow maps to provide the long-distance shadow rendering with minimal impacts to accuracy. As we dynamically position the sun and its corresponding directional light, we can project these shadows over hundreds of kilometers of terrain with very little impact to performance. The use of both Nanite in coordination with virtual shadow maps on smaller objects such as rocks allows for scalability. Another feature of Unreal Engine 5 is the use of double precision in the scene graph. This allows us to use SPICE, a JPL ephemeris tool that provides the position and orientation of planetary bodies and spacecraft with respect to time and relative to an observer. The double precision capability allows us to render these planetary bodies to scale and position them with actual relative positions to the lunar planet fixed coordinate system. This provides us the ability to have higher fidelity predicted lighting conditions based off sun and earth positions, and improves the accuracy of our generated terrain. Additionally, we can add spacecraft and their corresponding orbits or trajectories as part of our simulation. For example, we can include the Gateway in its near rectilinear halo orbit, or something like the HLS lander in its translunar injection or descent phase to the lunar surface. Some additional features of Unreal we are able to leverage for our simulations include the ability to have multiple infinite light sources. With this, we can not only include the effects of sunlight, but as well as earthshine, which is many times brighter than a full moon in its full phase on Earth. World partitioning and Nanite help improve performance of our large rendered scenes, and features like N-Display and pixel streaming provide us the opportunity to augment our simulations and integrate them into facilities like a video wall or build them into tools for remote operation. So Unreal Engine 5 has allowed us for a huge advancement in the development of our render-based simulations and visualizations. Our workflow from taking authoritative LRO DEM data and producing accurate lunar terrain has explored several different methods, and each with its own merits and trade-offs, depending on its intended use. And our lunar surface environment modeling fidelity has benefited greatly from these unique features present in UE5. All right, thank you, and we'll open it up for questions.